As promised, example numero dos. Live from my house. A hot cup of tea. You know Keshko and their hot tea. We're good at that. Spilling tea all day long. Anywho, a hot cup of tea is decreasing in temperature. I cracked myself up. At a constant rate of 21. Oh, geez, Louise. All right. Well, thanks for that, computer. Decreasing in temperature. So again, decreasing, telling us that we're going to be seeing decay, or we're going to be using the subtraction sign of that formula. At a constant rate of 21.25% per 5 minutes. Woof. Okay. So first off, need to point it out. Even though it says a constant rate, this is still not linear. Percentages are not a constant. Percent is not a constant rate of change. A constant percent is not a constant rate of change. So anywho, we need to take that gobbledygook percentage and we need to turn this into a unit rate. Turn into a unit rate. And lucky for you, if you don't remember how to find a unit rate, I did this with my 7th graders not too long ago, so it's fresh in the brains. You use division to find a unit rate. You know, that how many what per what. So if we have 21.25% per, your fraction bar is like that word per 5 minutes. I want to find out for how many for 1 minute. What percent per 1 minute? So just going to do that little bit of division. 21.25 divided by 5 is 4.25% each minute. Now I want to pause and take a point and point this out here. Number 2 here. So here they're saying that you have 12% per 30-minute period, but because of this key piece right here, where T is the number of 30-minute periods, you do not need to do any finding of the unit right there. You can just use that as is and move on with your life. So now you know. Okay, so I'm going to use that to create my equation, that y equals my initial 1 plus or minus percent over 100 to the t time. I just like to rewrite it because it's important for me. Y equals initial value. The cup is currently 200 degrees, so initial value is 200. We're using a decay, so we're using the subtraction, 4.25% to the t time. I'm just going to do a little bit of math. 4.25 divided by 100. 1 minus that leaves me with 95.75. So y equals 200 times 95.75. That's a decimal. Raised to the t time. And again, I'm just going to take one more step and turn that into function notation. If I have any say in it, you will not lose credit if you don't write this in function notation. But rather be safe than sorry. Okay, boom. So then the next question, how long will it take for the T to be at 150 degrees? So in theory, you might think that we can take that 150 degrees, plug it in for the temperature, and solve. So while you are absolutely right, that is the process that you would need to go about doing this. You do not know how to solve an exponential equation, though, and that's not something you are learning until Algebra 2. So that's an Algebra 2 topic. We, to figure this out, are just going to use the calculator. We're going to use the table to find when y is equal to 150. Because that is us being resourceful. We don't know how to solve for this, so we're going to do the best that we can to get around that. 0.9575 caret. Remember, whenever you're plugging something into y equals, you are always keeping the x as a variable, or the time as a variable. Okay. I don't know. I feel like I didn't plug that in correct. 200. No, I did. Okay. Nope. I'm not being patient enough. Okay. Okay, so 150. Does it tell to the nearest minute? So 150 happens somewhere between 6 and 7, but I might not be sure about which one. So we can go to my table start and we can change what my table goes up to by, 0.5s. And maybe that will give us a little bit better of a view. Okay. Oh, so right there at 6.5, it's just a little bit over 150. So 6.5 would round to 7 minutes. So 7 minutes approximately. Boom sauce.